Hello and welcome to this virtual meeting. For the next 15 minutes or so, I will be showcasing major results on the use of bioelectric responsive biomaterials for accelerated and scarless wound repair. Let us first understand the concept of bioelectricity. Bioelectricity refers to electrical flow in the body, and it plays a significant role in many physiological processes. In fact, without bioelectricity, one would not be able to read messages from one's mobile phone. And it is not because there is something wrong with the phone, it's because your brain would not work. Everything we do is controlled by electrical signals running through our bodies. The skin also has bioelectrical activity, which, although small, can be measured. In fact, normal human epidermis possesses a transepithelial potential, which varies depending on the location. Following skin injury, the transepithelial potential is disrupted, and this induces an endogenous direct current electric field which is directed towards the middle of the wound, as indicated by the direction of the bold green arrows. This endogenous electric field initiates the wound healing cascade and stimulates the migration of cells such as fibroblasts and macrophages. The wound healing cascade consists of three main phases, namely the inflammatory phase, the proliferative phase, and the remodeling phase. In the first phase, a clot is formed to stop the bleeding. Macrophages then migrate to the wound site to clear debris and remove bacteria. The proliferative phase consists of filling and covering the wound with granulation tissue. Fibroblast and keratinocyte proliferation is enhanced and endothelial cells migrate to the wound. In the remodeling phase, the new tissue formed gains strength and collagen fibers reorganize themselves. Before moving to the next slide, let me warn you that it contains sensitive photos. Diabetic foot ulcers are a major health issue in Mauritius, where 20% of the adult population suffer from diabetes. Diabetic foot ulcers are very slow healing and often take years to heal. In most cases, they do not heal at all, leading to amputations. Several commercial products are available for treatment of diabetic foot ulcers. One of them is Matrederm. Matrederm is a dermal substitute consisting of collagen and elastin. These images show a diabetic foot ulcer which did not heal for more than 3 years. The patient received treatment with Matrederm, and after 5 days, we note the formation of granulation tissue. After 24 months, the wound closed completely. On average, treatment of diabetic foot ulcers with Matrederm cost around €1,000, which is very expensive and therefore cannot be afforded by everyone. We therefore propose the use of a bioelectric responsive nanofiber-based scaffold for skin regeneration. The scaffold was fabricated using the electrospinning technique and consisted of polydioxanone (PDX) and polyhydroxybutyrate valerate (PHBV). PHBV is a piezoelectric polymer. In other words, in vivo implantation of the latter will induce an electrical response due to mechanical movement of the host. As noted from the table, the contact angle of the first 3 scaffolds could not be measured. This indicates that in these scaffolds, PDX was located at the surface of the fibers, while in the remaining compositions, PDX was located within the fibers. Since inflammation is crucial for wound healing, we assessed the in vitro inflammatory response of the scaffolds with mouse macrophage cells. Addition of PHBV to PDX led to morphological changes in the macrophages. As noted from scanning electron microscope images here, macrophages cultured on low PHBV content mats displayed smooth and rounded shapes, while on high PHBV content they showed rough, ruffled surfaces. The cell surface area was also found to increase with increasing PHBV content. The concentration of TNF-alpha produced by the macrophages when seated on the scaffolds was also measured by ELISA. We noted that the concentration of TNF-alpha decreased with increasing PHBV content above 28%. Overall, these results suggest that the addition of PHBV promoted macrophage polarization to the M2 phenotype. Fibroblasts play a crucial role during the proliferative and remodeling phase. We therefore investigated the proliferation and migration of fibroblasts. As noted from the figure on the left-hand side, addition of 50 to 80% PHBV to PDX led to substantial increase in cell number after 7 days. That is, addition of PHBV promoted fibroblast proliferation. Fibroblast migration is critical to close the wound following an injury. In fact, insufficient cell migration results in poor or delayed healing. Interestingly, incorporation of PHBV within PDX favored fibroblast migration. In fact, the 2080 composition led to highest number of cell migration. Excessive contraction in wounds lead to scarring, and it is caused by fibroblast cells. We thus analyzed the percentage scaffold contraction as a measure of the external deformation of the scaffold caused by the cells. Blends of PDX and PHBV led to reduced scaffold contraction as compared to PDX and PHBV. This indicates that PDX and PHBV blends are more likely to reduce scarring by resisting to the contractile forces exerted by fibroblasts. In vivo biocompatibility studies of the scaffolds confirmed that they were all non-toxic. Histological analysis of the explanted scaffolds and tissue indicated that electrospun PDX scaffold showed signs of degradation. The 70-30 scaffold also started degrading, as noted by the thinning of the bottommost scaffold layer. On the other hand, the 2080 and PHBV scaffold showed no signs of degradation. In general, all scaffolds showed some degree of cellular infiltration, but the mechanism and pattern varied. In addition, significantly less cells infiltrated the PHBV scaffold compared to the blend mats. After 2 weeks, we noted the formation of a fibrous capsule around all scaffolds. Pure PDX led to enhanced fibrosis, while addition of PHBV to PDX reduced the thickness of the fibrous capsule, suggesting better scaffold integration with the tissue. Based on in vitro results and in vivo biocompatibility tests, the 2080 PDX PHBV mat was chosen for further in vivo wound healing studies. The scaffold was loaded with 3 different additives, namely hydroxyapatite, curcumin, and fenugreek oil. Briefly, full-thickness wounds of 6 mm diameter were created on the dorsal region of Wistar rats. The hydrated scaffolds were placed on the wounds, which were then covered with gauze and dressing. The rats were followed for a period of 3 weeks, and photographs of the wounds were taken regularly. The wound diameter was also measured over 3 weeks. We noted that the negative control and the wound treated with PDX healed very rapidly, whereby almost 50% of the wound was closed by day 7. On day 7, the negative control wound started contracting significantly, losing its circular shape and becoming star-shaped. On the other hand, wounds treated with the 2080 scaffolds healed at a slower rate, indicating reduced contraction. We also calculated the remodeled epithelium, REL, and proliferative epithelium, PEL lengths for different scaffold-treated groups. We found that the REL, that is the remodeled epithelium length, was higher for all scaffolds in contrast to the negative control and pure PDX, suggesting that the 2080 blend scaffolds favored granulation and skin remodeling. Extracellular matrix remodeling is a critical distinguishing feature between tissue scarring and regeneration. The distance between collagen fibers in the newly formed tissue was measured. We noted that collagen fibers were tightly packed into parallel fibril layers in the negative control and PDX-treated groups, while in the 2080 scaffold-treated groups, the fibrils were less organized and distributed haphazardly with more space in between the fibrils. These results indicate better extracellular matrix remodeling in wounds treated with the PDX-PHBV blends. Therefore, to conclude, we successfully fabricated electrospun nanofibrous mats consisting of polydioxanone and polyhydroxybutyrate valurate. We also showed via in vitro studies that addition of PHBV to PDX led to fibroblast proliferation and migration, promoted macrophage polarization to the pro-healing phenotype, and promoted keratinocyte proliferation. In addition, in vivo studies involving wound-healing rat models showed that the PDX-PHBV blend mats accelerated wound healing and also led to scarless wound regeneration. With this, I would like to thank you for your kind attention.